Okay, this is the last worksheet in chapter 5, the review. There's 4 problems, but they got lots of parts. This first one is a three-way Venn diagram, which we haven't done, but it's not that much of a stretch to just adjust from a two-circle Venn diagram. And it's about people's choices for what they're going to eat. They have appetizers, desserts, and an entree. The person can have one, two, or all three of those. So the people in the very center had all three. This football shape here are people that had both appetizers and dessert. So that would be 129 people that had an appetizer and a dessert. These 4 people, they they only had an appetizer and a dessert, while these 125 had all three. All right, part A. Probability someone had all three. Well, first thing is I added up all the people. You can see my calculator there. Some of them ran off the edge, but I did it twice to double check my work. And I have 276 people, and 125 people ordered all three. As always, you want to make that a decimal? Go for it. 45% of the people. B, a person only orders one of them. Only one of them. So that would be these 3 that I'm highlighting in orange. And they're the only people that only had one item. 57 people. Okay. C, they ordered just an entree and dessert. So they had both of these. Let's change my highlighting color. Oh, I'll just delete those and start over. Just an entree and a dessert. So that would only be these. It's not these because it says just or like only is another word for that. Only an entree and a dessert. So not the 125 in the middle. 65 out of 276. A person orders 2 of them. Oh, a little bit more generalized. That would be, if I'm interpreting this correctly, that would be the 4, the 22, and the 65. I'm reading this to mean a person orders exactly 2 of them. It doesn't say a person orders 2 or more. So I'm interpreting it to mean exactly 2, which would be those orange numbers that I highlighted. So 91. Okay, those were just straightforward probability questions. The next ones are the conditions. You can do this by practically looking, or you can use the formula. So G says a person orders dessert given he orders an entree. I always like to circle the condition when I'm given a Venn diagram. In other words, my condition is that they ordered an entree. So, well, that's this entire circle. Everybody in this circle ordered an entree. Okay, so that is my sample, so to speak. I have to pick from somebody in that circle. So in that circle, there are this many people, 251. And of them, of those people, how many ordered a dessert? The dessert was ordered by this and this 125 and the 65. 125 ordered all 3, but they have a dessert. 65 ordered dessert and an entree. They did not order a dessert, and they did not order a dessert. So 122 plus 65 is 187. Out of, not the grand total, remember, out of 251. My total is that circle that I added up on the line above on my calculator. H, Oh, here, I know this. Well, this will help us later to go back for a minute. So this is about 74.5%. All right. H, it's the same condition, so it's the same denominator. It's 207, 251, right? It's the same circle, but now how many of them ordered an appetizer? So now my highlighted parts shift. The people in the middle ordered an appetizer, and so did these 22 people. So 125 plus 22 is 147 out of 251, which is 147 divided by 2, about 58.6%. Okay, let's do these next two with the formula in case you want to wrestle with that. Okay, the formula for G would look like this. The numerator would be the probability of an entree. I'll say int, and dessert, DESS, two S's because you always want two servings of dessert, divided by the probability of the condition, which is the probability of dessert. Okay. The probability that someone ordered an entree and dessert is how many people ordered an entree and dessert? Let me clear this off again. I like to start fresh. People that ordered an entree and or dessert, that would be these people ordered an entree or a dessert. I know the people in the middle ordered more, but they did order an entree and a dessert. So that is the 187 number again. 187 out of 276 divided by the probability somebody ordered dessert. For that, we have to add up the entire dessert circle. So that would be this plus this is 187 plus 8 is 195 plus 4, 199. 199 out of 276. Remember what we did in class, those cancel, and what we did in our previous lessons. So it's 187 over 199. H, let's do it with the formula. Numerator is the probability dessert and two of them. Ordering two of them. And the denominator is the probability of the condition, which is ordering two of them. Okay. Let me start over on my chart up here. So what is the probability that someone ordered a dessert and two of them? Well, I think that would just be this and this. And again, I'm interpreting this, when I read this, I'm interpreting this as like exactly two, all right? So I'm not including that middle group the way I'm reading it. Okay, and I try to avoid that on test questions so that you're not like, well, it's open to interpretation, right? I'm much more clear. So there's 69 of those out of 276. So 69 people ordered two of the items and they ordered dessert. And then you divide by how many people ordered the probability that they ordered two items. I would simply add into my coloring, my highlighted, I would add these in. So I've got 65 plus 4 plus 22. 91 of the people ordered two of them. And that's 91 out of 276. The 276's go gone again. And my answer is 69 over 91. All right. Are ordering an appetizer and a dessert independent? If they are, that means that if I order a dessert, it has no impact or no influence on my probability of ordering an appetizer, and vice versa. And we're going to look at the numbers. So the probability, there's a formula. The probability of an appetizer, given that you ordered dessert, if they're independent, if you put a question mark here, if this is true, if the dessert order has no impact on the appetizer order, then this will equal the probability of an appetizer by itself. Okay, if it's true. So we need to find this out. So we don't have this figured out yet, do we? I'm looking up here. I don't think it's one of these. Mm, no, it's not. So the dessert is the condition. So here's dessert. Okay. How many folks are in that dessert circle? Um, I don't know if I've added that up yet, so I'll do that. 125 plus 65 plus 8 plus 4. 202. All right. So my denominator is 202. Of the people in that circle, in this circle, how many of them ordered an appetizer? And that would be these four and these 125. So 129. It's going to help me to find a decimal approximation for this. 109, 129 divided by 202. So about 68%. Does that equal the probability of just ordering an appetizer? So for that, there's no condition. How many people in this chart ordered an appetizer? Again, I'm interpreting this to mean just any old appetizer. It could have been one, two, or three. And that is everybody in this circle. Okay. So I'm going to add up those numbers. 10 and 4 and 125 and 22. 161 out of 276. That's the grand total because there's no condition here. The grand total of 276. So that's 58%. Are they equal? No. So when it says explain, you can show your work, or you could say um, ordering a dessert does influence a person's choice or decision to order an appetizer. That makes sense, right? Maybe you're at the restaurant, order your appetizer or wings, and then they come by, and now you're full, you ate too much, and now you don't order dessert. I don't know. By the way, this, I should say, it doesn't matter which way you do this. If you switch these, that would also be fine. And it would also not work out. So it doesn't matter which way you go. Okay, comment on this claim. If a person orders an entree, he's more likely to order dessert than an appetizer. So my condition is ordering an entree. If that's the condition, are you more likely to get dessert than an appetizer? So in fact, we have already done the work. So right here we did it, and right here we did it. Because both of them have a condition of ordering an entree, and here's ordering a dessert, and here's ordering an appetizer. So is the dessert more likely? It looks like yes. We had 74.5% is greater than 58.6%. Got those from right here. and right here. Okay, so don't go back and start all over. 2, class has 10 girls. So I've already filled the chart out. Take your time if you have questions. I think that's pretty intuitive though. Probability that you pick one person, one student, and that it's a boy. Pretty straightforward. That's 5 out of 15. That's 1/3. Probability it's a girl, 10 out of 15, or 2/3. The student is a passing boy. That's only referring to these 4 boys right there. So 4 out of 15. A passing girl, that is the 7 right there. The student is passing, so it doesn't specify boy or girl. So passing, we have 11. Failing, we have 4 kids. So those rattle off pretty fast. G, we got a condition. Given the student's passing. Okay. I'm going to just highlight the people that are passing. How many people are passing? 11. So that's my denominator. It limits my sample space. Um, of that highlighted group, how many are boys? 4 of them. All right, next question. Same thing, it says given the students passing, that's the same group. So it's still a denominator of 11, but now how many of them are girls? 7 are. Our condition changes, so let me change my highlighting. Now the condition is a boy. So now my highlighted portion I care about is this. There are 5 of them, 5 boys. And how many of them are passing? Well, 4 of them are passing. Okay, the next one is moves, it's just going to move my highlighted because my condition now goes from boy to girl. So now here's my condition. That's my new sample space of 10. How many of them are passing? 7 out of 10. So you could look at this and go, oh, 80% of boys are passing. And in this group, only 70% of girls are passing. So you could compare in that way. Okay, determine whether being a boy and passing are independent. So is the probability of passing, given that the student is a boy, the same as if it was just any student? That's the question. Okay. We already have this right here. Probability they're passing given it's a boy. We did that. That's 80%, so that's 0.80. Okay. And we already have the probability that any old student is passing right here, 11 out of 15. So don't go back, don't start over. I do need to check 11 divided by 15 to see, to see if it's the same. And it's not the same. 0.80 does not equal 0.73. So not independent. All right. Next, we have a class with 100 students, 78 boys. Let me make another chart for this one. Up here. Let's get off the color red. Don't like it. So boys, girls. The other categories are sports and not sports. Okay. Slick. Okay, 100 kids total. 70 are boys. All right, put 70 over there. That means 30 must be girls. 70% of the boys are in sports. So what is 0.70 times, oh geez, 0.70 times 70? 49. 49 play sports, therefore 21 don't play sports. For the girls, 40% of the girls are involved in sports. What's 0.40 times 30? That's 12 girls in sports. That means 18 don't. Let's add up and down as well. This is 61. This is 39. Just to double check, this plus this is indeed 100. All right. Part A, if the student's a boy, what's the probability he's in sports? So if he's a boy, there's 70 of those. And of those 70, 49 are in sports. So it's 49 out of 70. Part B, if you read it carefully, there is no condition here. This is just pick any old kid. What's the probability they're in sports? 61 out of 100 or 61%. C, here's the if is the condition. If the kid's in sports, okay? So that's this group. So there are 61 kids to choose from. What's the probability that he's a boy? So 49. 49 out of 61. D, probability a student is a boy or involved in sports. No condition here, but we do or a couple ways. You could just highlight the kids that are a boy or they're in sports or both. That would be this number, and this number. Those sections are boys or they play sports or both. And then you add them up. And that would add up to 82, okay? 82 out of 100. The other way to do it is, let me highlight in other colors. Well, I'll just take away my orange. Is to say, okay, I've got 70 boys, I have 61 kids in sports. So you would go 70 out of 100 plus 61 out of 100. But if you stop there, you're at over 100. You subtract, remember, probability of A plus probability of B minus the probability of A and B. The probability of A and B is the 49. You don't want to count these people twice. These 49 people are included in the 70. They're also included in the 61. So you got to subtract 49. And you'll get the same thing. You'll get 82. All right, determine if being involved in sports is independent of being a boy. So if it is, then the probability of sports is not affected by being a boy or a girl, is essentially what this is asking. Um, so the probability of sports given a boy, if the probability of sports is not affected by this condition at all, then this will just equal the probability that the kid plays sports. Okay? And we already have these, I believe. If the student's a boy, what's the probability he's in sports? Right there, 49 out of 70. That's this side. Does that equal the probability that a kid plays sports? Oh, look, that's right here. That's 61%. I suppose I should divide to find out. Ooh, it's close, 0.70, but that is not equal. So they are not independent. Another way to say that is like the proportion of girls that play sports is not the same as the proportion of boys that play sports. So they're not independent. Last one, tree diagram. Um, it is estimated 4% of people who spend time in the woods will get Lyme's disease. Of the people with Lyme's disease, the test to determine if you have it will give a positive reading 97% of the time. Of the people who do not have it, the same test will give a negative rating 92% of the time. Make a tree diagram for this problem. All right, so let's start with the first part. 4% of the people who spend time in the woods get Lyme's disease. Okay, so the majority do not get Lyme's, we'll say, and that is 96% of people. And 4% that spend time in the woods get limes. Remember, every branch, when you have a split, your percentages must add up to 100. Okay? Now, what does it say? This is where it gets a little bit crazy. Of the people with limes. Okay, so that's this branch down here. They're going to take the test. Sometimes the test will say positive, and sometimes it will say negative. Okay. Um, of the people with limes, they take a test, and it will have a positive reading 97% of the time. So we'll say 0.97. We'll put a plus for positive. Well, then again, if this is 97%, this is the remainder from 100. So this would be 3% of the time you get a negative reading. Okay, so if you have Lyme's disease, you take the test, 97% of the time it will be accurate because you have Lyme's disease. 3% of the time, this is a problem. It tells you it's negative, but you actually do have Lyme's disease. And we know with all these COVID testing we've been doing lately, this happens. All right, then up on the top, what are the percentages? Same thing. You're going to have these people take a test. Sometimes it's positive and sometimes it's negative. That's the sentence. Of the people who do not have Lyme's, it will have a negative rating 92% of the time. A negative rating 92% of the time, which means this is 8% of the time up top. Okay, there you go. I constructed it. Um, then I'm going to find the probabilities of all four of these branches by multiplying, right? Like what's the probability of this one? It's 0.96 times 0.08. So I'm sitting at 0.0768. Then I'm going to do 0.96 times 0.92. 88% of the people. Oh, let's leave it at 88. 0.02 times 0.97 is 0.0194. I don't know why I did more decimals there, but not there. There we go. And 0.02 times 0.03. I could have done that in my head. That's 0.0006. Very small. All right. What's the probability someone gets a positive reading? That would be this one and this one added up. 0.0768 plus 0.0194. That's a lot of positive readings. That's almost 10%. 0.0962. That's a lousy zero, Fig. There we go. B, that the person has a negative reading. Well, couldn't I just do 1 minus the answer I just got? Sure, why not? Or if you'd rather, you could add up this plus this, which that doesn't look right to me. Like I missed something. Hmm. I don't know why I don't like that. Makes me think I made a mistake. Hmm. I'm sure one of you guys will find it. Like what I'm looking at is why doesn't like see that doesn't add up to what I found this way. Oh, you know what it could be? It could be a rounding error. Like these are rounded off. Okay, let's do that. Let's just take these two instead, like I did there on the calculator, and go with those 0.8838. So rounding does matter. See, if the person gets a positive reading, he has Lyme's. Okay, so now we got a condition here. I'll do shorthand like this. Has Lyme's given a positive reading? So the formula is the numerator is Lyme's and positive reading. The denominator is the probability of a positive reading. And I have the numerator calculated right here. It's Lyme's and positive. That's 0.0768. And the denominator is positive reading, which I found right here, 0.0962. And then divide them. About, let's say, 79%. Okay, moving on. See if we can streamline this. We've done so many. If a person gets positive reading, he doesn't have Lyme's disease. So in the numerator, I want the probability of positive and Lyme's. The denominator is the probability of my condition, which comes after the if, which is a positive reading. So that's the same denominator as the one I just did. But now my numerator is positive and Lyme's. Oh, wait a minute. Yeah, positive and this is what I just did, isn't it? I think I might have messed up part C. Or these are just going to be the same answer. Oh, sorry. He doesn't have Lyme's disease. Hello, Fag. So not Lyme's disease. There we go. Not Lyme's disease. Oh yeah, I did. Even with that, I did it backwards. I must be tired. Over here, when I pulled this number, this is the number of people that do not have Lyme's, which is what I wanted here. So in fact, I'm going to swap these. This one's going to go over there. And this, what I found here, this is the answer over here. And then this guy comes back over here. I hope I'm making sense, right? This here is the probability that someone has a positive test and they do not have Lyme's, which is right there. Okay, so I had these flip-flopped. This is the probability you have Lyme's and a positive test, which is 0.0194. Okay. So about 20%. All right. E. Now the condition is a negative reading, right? So now my denominator is the probability of a negative reading, which is right here, which is 0.8838. My numerator will be the probability of both of these. A negative reading and you have Lyme's, that's this one, 0.0006. So remember, scientific notation means you take that decimal and you move it. It says times 10 to the negative 4, right? So you move it 4 places, 1, 2, 3, 4, put your new decimal there, fill in the zeros. So in other words, not very likely. 0.00678. Okay. I don't. It seems really small to me, like something's wrong. Um, if a person gets a negative reading, that's this, which is that. He doesn't have Lyme's. So the numerator should be the probability that you don't have Lyme's and you have a negative reading. Oh, there we go. That makes much, much more sense. Right? My numerator is the probability of both of these conditions, both of these things being true. A negative reading and not having Lyme's, doesn't have Lyme's, doesn't have Lyme's. Negative reading is this number. I chose the wrong one. A little more prep would be a good idea, Flag. Thank you. 8838. And this is going to be, look at that, really strong. 99% of the time. 99.9%. That makes more sense. Makes me feel better about the test, too. All right, last condition here. If you have a negative reading, okay, that's the same denominator as the one we just did. But now you have Lyme's disease. So my numerator is you have Lyme's and a negative reading. So this is the one I was doing just further ago. And I had that on my screen. That was the 0.000678. It's not likely. Okay. In other words, if you have Lyme's disease, you're probably going to get a positive reading. All right. G and H are like follow up. If you tested positive for Lyme's disease, you probably need a second opinion. That would be these. If you tested positive, right? Well, if you tested positive for Lyme's disease, should you get a second opinion? How reliable is the test? It says here, if you tested positive and you have Lyme's disease, oh my gosh, I think these don't look right to me. Again, let me shore these up. So, did I do this right? A positive reading is my condition, and that would be this plus this, which is 0.0962. That's good. And then my numerator would be the probability of Lyme's and a positive test. Yeah, okay. So, this is going to help me better. If you tested positive for Lyme's, you probably need a second opinion. So, these are false positives, meaning these people don't have Lyme's, but they had a positive test. This was a correct positive. Okay. So if you tested positive, would you be very convinced that you do indeed have it? Well, if you don't have Lyme's disease, look at this, 7 to 8% of the time, you're going to get a positive result. Um, so I would say 7 to 8% of tests for people without Lyme's, people that do not have Lyme's disease, give false positives, which is to me is really high. So yes, I'd like another opinion. Yes, I would retest or get a second opinion. Okay? I'd like to know for sure, do I really have it? All right. Then the last one, if you tested negative for Lyme's disease, go get a second opinion. So that would be these two. So if you have Lyme's, but it gives you a negative test, that's called a false negative. It tells you you're negative, but you actually have it. This would be the problem, right? This one here is a correct negative. So again, the false negative and the false positive is the one we're looking at. The false positive this is really high, 7 or 8% of the time. This false negative is pretty much zero. So I would be pretty darn confident that false negatives do not happen. Okay. So false negatives only occur in 0.0006. If you want to change that to a percentage, it's still tiny. In 0.06% of people with Lyme's disease. So that's these people have Lyme's, but the test for some reason was negative. That almost never happens. Um, so a second opinion isn't really necessary. All right, thanks for bearing with me through that, you guys. I didn't prep as well as I should have. Bye bye.